Hi there, we're Team Giraffe, and this is our presentation on image thumbnail generation. So our problem is to generate thumbnail in real time, given any size and aspect ratio for an input image. The use of thumbnail image definitely facilitates easy browsing because it provides a smaller version of the original images that effectively capture and represent the original content. Our work is practical in such a way that it can replace time-consuming and quality unguaranteed manual hand-picking process of creators. Furthermore, our approach was able to make the thumbnails generation for all on-scene settings realistic. Traditionally, this problem was solved by predicting a sequence map that specifies the importance of various regions and objects of the input image. However, what makes us different is that our model generalized two thumbnails of different sizes, including those with extreme aspect ratios, in a faster manner. In our task, we want to re-implement ResNet feature extractor with adaptive convolutional layer and extend by adding a global context aggregation layer and switching the 101 ResNet to VGG19 while using the dataset which contains 70,048 thumbnail annotations created on 28,064 images through Amazon Mechanical Turk.
One of the difficult parts is to find the target values to train our model. It is unrealistic to get all the possible aspect ratios for every photo. Thus, we need to be able to generate targets from one true bounding box for each image. For one aspect ratio, we created 3 different scales. We use these 3 different scales to scan the image to create the stack of possible subsections of the image. We calculate the intersection over union score. The higher the IOU score with green bounding box, more likely this subsection is a good thumbnail. As shown in this example, as we slide across the image, the IOU score drops. If the IOU score is above 60%, it is a valid thumbnail. If the score is below 30%, it is not. We sampled positive thumbnails and extract their coordinates to form the target bounding box for our model. We sampled another set of candidate bounding boxes. For positive thumbnail, we label the representative score as 1. For negative, we label as 0. This will be the target for the representativeness score prediction. This is the baseline model that we focused on before midterm. It is a combination of the 101 ResNet and adaptive convolutional layer to dynamically generate the kernels. After further research and study, we replaced the ResNet 101 with a lighter VGG19 model and complemented it with a global context aggregation part to better capture the global context when learning the image. The GCA part is used to generate an attention map over the global context for each pixel. This will increase the receptive field of the model to the entire image and enhance feature representability of the model. We utilized 4 recurrent neural network to scan an input image both horizontally and vertically along both directions to blend the context from the 4 directions. For adaptive convolutional layer, we used fully connected layers to dynamically change the weights of the kernel. The first set of kernels are used to generate the location of the bounding box. The second set of kernels are used to generate the representative score of boxes. For the bounding box prediction, we used smooth L1 loss. For representative scores, we used binary cross entropy loss. The 2 losses are normalized and weighted by lambda.
Coming to the result, here are some output examples. The original image is shown on the left with the generated thumbnails on the right. The user-defined aspect ratio is given in black and the aspect ratio of the generated thumbnail is given in red. The green bounding box is the ground truth while the red one is a prediction. Then as you can see, we use these 6 metrics for comparing. We also plotted the trend of all 6 metrics, and our latest implementation yields a much better performance than the baseline model in all different metrics. I'd highlight that the decreasing trend of center offset slows down at around 18 epochs, as opposed to the new model decreasing at a steady speed, especially after 20 epochs, which results in a much better overall performance. Our model did significantly better in terms of IOU because with global context aggregation embedded, it has more robust contextual information. In conclusion, comparing with previous works, VGG19 and Global Context Aggregation layer enable the model to generate thumbnails under any user-defined aspect ratio, even for unseen aspect ratio, which greatly expanded the flexibility. The network is also significantly faster and more accurate than our previous implementation in all 6 metrics that we use in evaluation.